Now, let's get started revising Unit 1. Now, I've split the Unit 1 revision into two parts because it's relatively long. So in this part, we're going to study everything from measurements and motion or kinematics, forces, up until momentum. Moments or the turning effect and other chapters are in the next part, so part 2. Before we begin in earnest, however, I want you to know how to use these revision sheets. First, every chapter, yours will look a little bit different, but it's the same thing in it. First, every chapter will have a small list, sometimes a very long list, of things that you need to keep in mind. These are what the curriculum, this is how the syllabus is described in the syllabus or in the curriculum. So for example, in the first chapter, you're required to describe the use of rulers and measuring cylinders, to describe how to measure a variety of time intervals, to describe or determine an average value for small distances and short intervals and so on. So this is the part about measurements. If you flip on to mass or weight, you need to state that mass is you'll notice how everything is listed exactly as it is in the syllabus. This is not something I will read in detail with you. However, this is something I want you to use like a checklist, meaning once you're done revising, you need to go back to the checklist and then ask yourself, hey, do I understand that mass per unit volume is density and that's the equation? Yes, I do. Khalas, this is good. Do I know how to describe, how to determine the density of a liquid or a regularly shaped solid or an irregularly shaped solid? Do I know how to make these descriptions? Not really. I don't know what do you mean by regularly shaped. So you go in back and revise it. And once you do, you check it, you understand. Determine whether an object floats based on density. Yeah. I know that, things are less dense, float, more dense, sink, so good, and so on. So I want you to use these like a checklist as you revise to make sure that you understand everything. If there's a sentence or a line in the curriculum that you do not understand, then go back and revise that or ask me a question about it later. All right? So let's get started with the beginning of Unit 1. Starting with the basic quantities and measurements. So what's a quantity? It's a physical quantity that you can measure, essentially, something that exists in nature. There are lots of quantities, but let's focus on what we call the base quantities and their SI units. Base quantities are not derived or calculated quantities. So something like length or time or mass is a base quantity, but something like speed or density or volume, these are what we call derived quantities, right? For now, let's just look at the base. So these are your base quantities. Temperature is a base quantity measured in Kelvin. Now, I know we're going to use Celsius later on, but for now, the SI unit is a Kelvin. Then current is measured in ampere. It's a base quantity. You should also be familiar with these prefixes. Most of the time, like 95% of the time, you're going to use kilo, which means times 1,000, centi, which is divided by 100, milli, which is divided by 1,000. You also need to know what mega is and what micro is, and forgive me, I just forgot to add this, so add it yourself, nano, which means is a small n, which is dividing by 1,000, or times 10 to the power of -9. These are prefixes that you should be familiar with. So when I say nanosecond, I mean, if I say the value is 5 nanoseconds, it's 5 times 10 to the power of -9 seconds. Okay? Just memorize these. And by the way, it has a nice fixed ratio. Besides the centi, milli is your first prefix that's smaller, which is 10 power -3. Micro is 10 power -6, like dividing by 1,000. Nano is dividing by 1,000, so 10 power -9. If you go up above the centi, you have kilo, which is times 1,000, or times 10 power 3. Mega, which is times 10 to the power of 6. And if you're curious, there is actually something even larger, which is called giga, like gigabytes in your memory. And that's times 1,000, or 10 power 9. So there's a symmetry here. There's a big amount of symmetry here for all of the prefixes that you have. Okay? You will often only use kilo and santi and milli. You will not very often use the others. It does show up though. Like when a question decides to be a little bit challenging, it does use giga or mega or like nano or so on. Thank God there's no pico and so on, and tera and stuff. Next up, how do we measure lengths? To measure regular lengths, when I say regular, I mean up to a meter, use a ruler. If it's longer than a meter, use a measuring tape. If it's really small, so something like the thickness of a coin, the thickness of a wire, the thickness of a sheet of card or paper, we use a micrometer. We use a what? A micrometer. Okay? Good. Next. How do we measure the thickness of a sheet of paper? This is something very old but basic. And this is a technique that we will very frequently use, by the way, which is what? If something is too small, we get a lot of it and divide by its number. Again, if something is too small, like if I'm getting the thickness of a sheet of paper, or I'm getting the thickness of a wire, or the thickness of a coin, you get lots of coins or lots of papers, measure the thickness of all of them, then divide by their number. So if I measure these as 5 centimeters or so, and it's 100 sheets of paper, this means that one sheet of paper is 5 centimeters divided by 100, which is 0.05 centimeters. That's if I want one sheet of paper. Please keep in mind, a lot of students make this mistake. They divide 100 by 5. It is always the quantity on top and the number of things on the bottom. Again, quantity on top. So total time on top, total thickness on top, total mass on top, divided by the number of things, never the opposite. Okay, good. Next. Sorry, there you go. Let's talk about volume. What is volume? It's defined as the space occupied by an object, how large or small an object is. To measure volume, it also depends on the object you're measuring. If you're measuring the volume of a liquid, you just use a measuring cylinder. If you're measuring the volume of a solid, and when I say regular solid, I mean something that has a regular shape, a box, a cube, a cuboid, all right, a cylinder. All of these are regular shapes, and they have their own value. So length times width times height for a cuboid. The cross-sectional area times height, or something like a cylinder. Sure, you might not need to remember the area of a circle, but I'm sure you already do. It's pi r squared, if you remember. Okay. So remember that. It's area times height. It doesn't show up a lot. But that's if it's a regular solid. What if it was an irregular solid? So it's not a fixed shape. It's like a stone or my keys or something. We use the displacement method, which involves putting some water into a measuring cylinder, measuring the initial volume, gently putting the rock, for example, into the water and getting the new volume, and then subtract the two readings to get the volume of the rock. All right? But that's a rock you can't smell because it's not cooking anything. Sorry. That's a rock joke. Anyway, next, time. Time. What is time? It's something that you measure in minutes or seconds or hours. It's the passage of time. What you need to understand is not a definition for it. We don't define it. What you need to understand is how to convert the units of time. So for example, an hour is 60 minutes. A minute is 60 seconds. You need to know how to convert from hours to minutes, from minutes to seconds, and back. So remember that. That's times 60 this way, divide by 60 the other way. A very common question is, how do I measure the period of oscillation of a pendulum or anything that vibrates? It could be a spring that's going up and down. The period of oscillation of a pendulum, all right? is measured by measuring the time of 10 oscillations or 20 oscillations, then dividing the reading by 20 or 10 by the number. Remember, you have to repeat and take average. This is a technique that we often use to improve. This is more of a paper 6 thing, but we sometimes use it in paper 4 to improve the reliability of a measurement. So just to improve it a little bit. And then finally, as an extra precaution, if there's an extra 4th mark for the question, we reset our stopwatch before making any measurements. So before we start, we reset, measure the time of 10 oscillations, divide the reading by 10, repeat and take an average. Have a nice day. Now, there aren't a lot of questions that are exclusively measurement-based. And most of the questions that are measurement-based are often in paper 6. But sometimes we get a basic question where you need to describe certain measurements, okay? For the time being, however, let's move on to a slightly more important, arguably more important chapter, which is about weight. First, let's talk about mass. Mass is defined as a quantity of matter of an object at rest. So just the amount of matter in an object. Now, mass is measured often using a balance, and it's measured in a unit called kilograms or grams. That's easy, no problem. But the only extra technique compared to before that we need to keep in mind when measuring mass is how do I get the mass of a liquid? How do I get the mass of a liquid? Because the problem is, like, for example, I have a cup of tea here. I'm going to take a sip of tea. Oh yeah, that's a good cup of tea. But so the problem is, if I wanted to get the mass of the liquid or the tea, the cup has weight, or the cup has mass in this particular case. So I need to get the mass of the empty container. It could be anything. It could be a cup or a measuring cylinder or a beaker. Then pour the liquid in, then get the mass of the new liquid plus container and get the difference. So it's basically M2 minus M1, but the mass of the liquid with the container minus the mass of the empty container. This gives you the mass of just the liquid inside. Okay. Next, what is weight? Weight is the pull of gravity or the gravitational force on an object. The pull of gravity is an acceptable answer, by the way. So please keep in mind, there is a difference between the mass of an object, like how many kilograms it is, and the weight of an object. Weight is a force. So the pen falls due to the weight of the object. But the fact that the pen exists and it has, plastic inside and stuff like that, that's mass. That's the difference between mass and weight. Keep that in mind. We calculate weight using W equals mg, where m is mass and g is, you can just call it gravity, but the proper definition is gravitational field strength or acceleration of free fall. And it has a value of 9.8 newtons per kilogram, as long as the question has not stated otherwise. In the beginning of an exam, on the front page of the exam, you will find a statement saying, take the weight of 1 kilogram to be 9.8 newtons, in brackets 9.8, meters per second squared, because that's the acceleration of free fall by default on Earth. If we're on a different planet, the question has to give us the new weight or the new value of G. G is defined as force per unit mass. Okay. Let's solve a couple of questions. Look at the first one. An object in space, in a space probe above the Earth, weighs 3.5 newtons. The gravitational field strength at this height is 7. Look at this. So it's no longer on Earth. The question has to give me the new value of G, right? Has to give me the new value of G. The gravitational field strength on the Earth's surface is 9.8 newtons per kilogram. So wait, that's G on Earth and G on the probe. What are the mass and the weight of the object on the Earth's surface? Hold on. These are two questions. Don't treat this like a multiple choice question. These are like two separate questions. Let's start with this. What is the mass? Okay, we have the weight and we have G. in space. So first, m equals w over g, where w is 3.5 and g is 7. So I'll work that out. 3.5 over 7. This gives me 0.5 kilograms. Cool. But then, now that we have the mass of the object in space is the same mass of the object on Earth. So the mass doesn't change. The weight could change, but the mass doesn't change. Okay? So now we get to calculate the weight on Earth. So that's mg, which is 0.5 times 9.8. 0.5 times 9.8. That gives us 4.9 newtons. Do we have this pair of answers? Yes, we do. 0.5 is either A or B. 4.9 is B. So B is my answer. Next. Which statement about mass or weight is not correct? Okay, let's read these. Masses can be compared using a balance. Like I can put them on a balance to compare. Yes. Mass is a force. No. خلاص, that's your answer. But just in case, let's read the rest. Weights can be compared using a balance. Yes. Mister, no. A balance measures mass. Absolutely. But here he's not talking about measurement. He's talking about comparing. Because if two objects have the same mass, let's say 1 kilogram, and I put them on the balance, like one on this balance and one on the other, or on a beam balance, they will give you the same reading because they have the same mass. And if they have the same weight, W equals mg, also means they have the same mass or equal masses. Weight is a force. That's correct. So B is our right answer here. Nice. This was easy. Piece of cake. Let's move on to the next topic. Let's talk about density. I'm sure you all know, and I've done this joke before. Well, what's heavier, a kilogram of steel or a kilogram of feathers? I'm sure you've seen that video somewhere on the internet, and if you haven't, you're missing out. It's very funny, as far as I'm concerned. But density, like a kilogram of steel or a kilogram of feathers, they're both the same mass, so they both have the same weight, so they both will be equally heavy. That's fine. Okay? But what is density? The difference between a kilogram of steel and a kilogram of feathers is that the feathers take up a ton of space, whereas the steel takes up very little space. Because the density of steel is greater than the density of the feathers. Density affects not just mass, but volume. It's a ratio of mass and volume. So it's the mass per unit volume of a substance. The symbol for density is rho. So it's rho equals m over v. The greater the density of an object, the smaller it is, and the more mass it has. So it's heavy but small. The less dense an object is, the larger it is. So think of a balloon, and with less mass. So mentally in your head, more dense means small and heavy, like a metal coin. Less dense means large and light, so like a balloon, for example. Even worse if it's a balloon full of helium. It's going to float. Okay. How do we measure density? Easy. We measure mass and we measure volume. Just keep in mind if there are any special techniques that you need to use. Like, for example, if I'm measuring the density of a solid, a regular solid, there's nothing special here. Balance is used to get the mass. The volume, you measure the length and width and height to get the volume. Done. If it's a liquid, then you need a measuring cylinder for the volume. But to get the mass, you need to go back and use that old technique over here. To get the mass, you need to get the mass of the empty container and the full container, get the difference. So this isn't really a question about density. It's using your old knowledge of measurements. How do I get the density of an irregular solid? Well, since it's a solid, you can just put it on a balance. And then that's the mass. But to get the volume, you need to use displacement. Get a cylinder with some liquid, that's V1. Put the object inside, the volume increases, that's V2. And that gives us the volume. And then we can calculate density using mass over volume. So all of these are easy. Next up, please note that density affects floating and sinking. It doesn't just matter if it's an object floating in water or sinking in water. Keep that in mind, okay? It could be liquids on top of each other, not just solids in liquids. But the less dense, like if you have a liquid and you have an object that's floating in it, that's because this object is less dense than the liquid, or the liquid is more dense. If you have an object that sinks in a liquid, the object is more dense, okay? Most challenging questions often involve liquids floating on top of each other. Like if I tell you, hey, and this was a question asked before, here are 3 liquids that we poured into a cylinder that don't mix. The liquids are called X, Y, and Z. Which one is the least dense liquid? Clearly what? X, right? Because it's floating. Which is the more dense liquid? Z. And Y is between the two. Okay? Now, a couple of very important points to keep in mind when you're solving anything regarding density. If I ever say the term objects are made of the same material, keep that in mind. This means the object have the same density. I don't care about anything. If I say they are made of the same material, they have the same density. Have a nice day. But second, and this is from thermal physics, but I'm using it now. Temperature changes density. How come? Remember that we have thermal expansion as a phenomenon. If the temperature of an object increases, the volume of the object increases, but the mass stays the same. So the density decreases. So heating makes an object less dense. If the temperature of the object decreases, like we cool it down, the volume of the object will also decrease. The mass stays the same. Mass will not change. So the density increases. It becomes more dense. So it sinks. That's why hot smoke rises, whereas cold vapor, like if I open up my freezer and get some ice, and you see this cold vapor that sometimes condenses as it leaves the freezer, it sinks because it's cold. It's more dense, so it sinks. Okay? Let's solve this question over here. A rectangular swimming pool is 50 meters long, 25 meters wide. That's length and width, by the way. So I'm probably using that. It contains water at a depth of 2 meters. That's height. The word depth or thickness can be used for height. The density of the water is 1,000 kilograms per meter cubed. What is the mass of the water in the pool? Again, ignore the fact that this is a multiple choice question. Calculate this normally. Density is mass over volume, which means mass is density times volume. But in this case, the volume is not given, but you do have the length and width and height. So it's actually length times width times height. So it's 1,000 times 50 times 25 times 2. So 1,000 times 50 times 25 times 2, which gives me a very big number. 2,500,000. Now, honestly, usually with these questions, I prefer to write it in standard form. But because this is a multiple choice question and that answer is there, I'm just going to choose it. But I would prefer to change it to standard form. Okay, very good. Next. We're now done with what? With the basic quantities and measurements. Okay. Before we move on to motion or velocity or speed or anything like that, let's quickly discuss scalars and vectors. There are 2 types of quantities in the world. We call them scalars, which are quantities that have only a magnitude, like distance and speed and time and mass. These are things that do not have a direction. Vectors are quantities that have magnitude and direction. If you don't internally understand what that means, it means that without a direction, you don't know what it's doing. Like if I tell you I'm 180 centimeters tall, I wish, but if I'm 180 centimeters tall, do you need a direction to know what that means? No, that's my height. I don't need a direction. If I tell you that I have a mass of 70 kilograms, I'm heading there. I'm on a diet in Ramadan. If I'm 70 kilograms, do I need the direction to explain what's going to happen to me? No, that's how much my mass is. I was about to say how much I weigh, but true. But if I tell you, uh, my little cousin decides to push my chair and I just stop, you don't know where I'm going, right? Because he could push my chair to the right and I move to the right. He could push my chair to the left. So even if I say it's a 2000 Newton force, I'm going to be shot out of my chair. But without the direction, you have no idea where I'm going. So a vector is a quantity that has direction. Okay? Things like forces and weights and velocity and acceleration and momentum, all of these have a direction. So they're considered vectors. Now, when it comes to representing vectors, I need you to keep in mind that most of the time, questions will just draw, arrows, right? Left, right. Sometimes you have the cardinal directions, north, south, east, and west. So these are all acceptable directions. Very rarely, however, will a question use a sign convention. And I honestly don't explain this often, like I don't use this in explanations often, but unfortunately in a very recent exam, a question used positive and negative signs to show you direction. Often if I say that a vector is positive, it means it's usually going to the right or going up. If I say it's negative, this means it's going to the left or going down. They have to be two opposites, however. So if I tell you, you have a ball moving with a velocity of +3, that's like me saying it's moving to the right with a speed of 3. But then it hits a wall and rebounds with a velocity of -4. I don't care how correct the values are. What's important is that if I erase the arrows, the positive and negative sign should also mean the direction has changed. It was moving to the right and then to the left. Maybe it's moving to the left and then it's to the right. The important thing is that it has changed. Capiche? Capiche. How do I find the resultant vector? Questions in chat. How do I find the resultant vector? Well, an easy thing to do is just to add or subtract. If you have two forces, like a force to the right, like a 10 Newton force to the right, and another 10 Newton force to the right, the resultant force is their sum. It'll be 20 to the right. If it's 10 to the right, but 3 to the left, it'll be 7 to the right. So forces that are in the same direction, you add them. Forces that are in opposite directions, you subtract them. Okay? But then sometimes the question will give you forces like this. F1 is a 10 Newton force to the right. F2 is a 10 Newton force to the top, often either drawn or described. Now, the resultant force will never be to the right or up top. It has to be somewhere in between. So we need to find that somewhere in between. And what we will use is a combination of trigonometry and Pythagoras. So first, like the rules are in front of you, but let's solve an example right away, like a quick example. Let's use this as my example. If I tell you you have a 10 Newton force to the right and a 10 Newton force up top, I want you to find the resultant, which is in between them. Let's call this R. You need to understand that any two forces at right angles to each other, constitute a triangle. Like if I draw them head to tail, they basically make a triangle. Like if this is R, this is the 10 to the right, and this is 10 to the top, and it's a 90-degree triangle, which is why Pythagoras works, which is why Pythagoras, the Pythagorean theorem, will work. The resultant, R squared, is equal to 10 squared plus 10 squared. But if I want R, I'm going to square root the whole thing. So square root 10 squared plus 10 squared under root. So square root 10 squared plus 10 squared, and that gives us 14.14. Just going to say 14 newtons. So it's not a pure addition. It's not going to hit 20 ever, by the way. But it's somewhere in between, 10 and 20, somewhere. But then how do I find the direction? Because remember, we said that vectors involve what? Directions. Now, in basic terms, directions are either left, right, up, down, north, south, east, west. But here, the direction has to be what? An angle. Because it's at an angle somewhere. Like if I tell you, and I'm like spoiling the answer, if I tell you that this is at a 45 degree to the horizontal, you know exactly where that vector is. It's like 45 degrees above the horizontal. But how do we get this angle? Like, how do we get this? Well, first, you need to understand that there are two possible angles that you could get. You could either get, let me erase this. Actually, I should just undo. You could either get this angle, let's call this theta 1, and you can either get this angle, theta 2. Which one do I get? Depends on the question. If the question says, find the direction of the resultant force relative to the horizontal, which is 90% of the cases, I mean theta 1, like the angle between the resultant and the horizontal. Okay? If I ask you, what's the direction relative to the vertical? Then I get the angle theta 2. Questions will always tell you which angle do they want. So there's no confusion there. You just need to read the question carefully. Okay, mister, now that we know that we need theta 2, theta 1, how do I get it? How do I get theta 1? Remember how I said this is an angle and trigonometry will work? Your basic trigonometrical functions are what? Sine, cosine, and tan. Where sine is the ratio, sine the angle is the ratio of the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. And tan is the opposite over the adjacent. My personal favorite to use is tan. Why? Because I don't need to find the resultant to get the angle. Like I can get the angle as a separate answer. Even if I couldn't, let's say I forgot Pythagoras, I can still get the angle. Okay? So tan theta, for example, is opposite over adjacent. But you might say, but I'm confused. I don't know how to draw a triangle in order to get the adjacent or the hypotenuse or... calm down. Always start with the adjacent. It's easy to identify. Adjacent means, I look like an Italian doing this. Adjacent means next to, right? So theta 1 is the angle next, or sorry, the adjacent is the vector next to the angle. So the arrow that's stuck to the angle, that's your adjacent. So the other thing is your opposite. So the other quantity is your opposite. Now, in this example, it's quite easy. It's like tan theta equals 10 over 10. Like I chose an easy one on purpose, but we're going to solve a question now using different vectors and using different values. Now, please remember, I want theta, not tan theta. So make sure to tan to the power of -1 the answer that you get, or the fraction that you get. You do that by typing shift tan on your calculator, and then 10 over 10. That gives me an angle of 45 degrees. Now, before I move on to solving an example, like a proper back question, there was a question here. How do you know if the direction is upwards or to the right? The question has to tell you what's going on. The question has to start by saying, oh, a ball is moving to the right, or a ball is moving horizontally at the speed of +3. Well, it's moving to the right with 3, and then when it rebounds, it's moving to the left with 4. Okay? Good. Let's solve an example. A boat crosses a river. I chose one without a diagram because I want you to sketch, by the way. It's always good to sketch. A boat crosses a river. The boat points at right angles to the river bank and travels at a speed of 3.5 2.5 meters per second relative to the water. Meaning what? If this is the water, like if this is the river, these are the banks, you're looking from the top. Your boat is trying to go up this way, right? And it's moving at a speed of 3.5 meters per second. A river acts at right angles to the direction that the boat travels. Now, I don't care if it's right angles to the right or to the left, it doesn't matter. But this means that the water is pushing the boat to the right, for example, at 2.5 meters per second. It won't matter if it's to the left, at least for now. The river has a current speed of 2.5. Cool. By drawing a scale diagram or by calculation, my favorite method is always calculation, determine the speed and the direction of the boat relative to the riverbank. First, let's deal with speed, and I'll go back to direction. Here's the sketch I want you guys to do. It's a 2.5 meters per second speed to the right. It's a 3.5 meters per second speed to the top. The resultant is somewhere in the middle. How do I find the resultant? So the resultant is equal to square root 2.5 squared plus 3.5 squared. Always square root these two vectors. So square root 2.5 squared plus 3.5 squared. This gives me 4.3. So the speed is 4.3 meters per second. Do not forget the units. Please, for the love of God, stop forgetting your units, okay? Cool. Now, what about the direction? He wants the direction of the boat relative to the riverbank. What's the riverbank? Remember, he said the boat points at right angles to the riverbank. This is the bank, which is the horizontal, because the boat is moving vertically, for example, in this case, and the bank is horizontal, which means I want the angle between R and the 2.5, which is the direction of the river. Riverbank, river, same thing. So tan theta equals opposite over adjacent. Remember, adjacent first. Adjacent is the 2.5. It's the one next to the angle. So the opposite has to be the other vector, 3.5. So theta is equal to tan power negative 1, 3.5 over 2.5. So shift tan 3.5 over 2.5, which gives me 54.46. We can just write that down as 54 degrees, and we have a nice night. Now, good question. Why is it always Pythagoras? Who said the forces are always perpendicular to each other? The syllabus. In 2023, the curriculum changed. And now any forces at angles to each other have to be at right angles. Determined by calculation the resultant of two vectors at right angles, limited to forces or velocity. Okay? Always. So again, how did we get the velocity? Velocity equals square root the two components squared. That's Pythagoras. I just used Pythagoras here. R squared equals 2.5 squared plus 3.5 squared. And then I squared it. That's the word. Next up. Speed is a scalar. Velocity is a vector. State the names of one other scalar and one other vector. Okay. We have a big list, but let's not cheat. What's another scalar? Obviously not speed. So let's use mass, for example. And for vector, let's use acceleration or force. They're both fine. I can't use speed and velocity because you already used them. Yeah. All right. So if you're asking what if it's a considered vector, what's considered a vector? You have a list of vectors that are accepted in this syllabus, by the way. That's your list of vectors that's accepted in this curriculum for now. Next, let's move on to motion. Mr. That's a big checklist. Yeah, I know. Remember, you're going to have to go through that checklist to make sure you understand everything. But let's get into the meat of the content. Starting with defining our most basic quantities. First, what is speed? Speed is distance over time. This one's easy. You don't need a lot of explanation for that. It's how fast you're moving. So it's distance over time. Sometimes use S, sometimes use V for velocity, because if you remember, velocity is speed in a certain direction. So it's the vector version of speed. But I don't care which one you use, V or S, when you're calculating things. How do I get average speed? Average speed is the total distance divided by total time. Now, the reasons we sometimes ask you for average speed is because maybe a journey consists of multiple steps, like I'm moving from A to B. I traveled a distance of, I don't know, 3 kilometers in half an hour. It's very slow, by the way. But then from B to C, I traveled a distance of 10 kilometers in half an hour. That's a little bit better. If I ask you for the average speed, I don't actually need an average of like speed of A, speed of B, speed of C. I don't add them, divide by their number. I take the total distance divided by the total time. Okay? Good. Next. Speed and obviously velocity has a specific graph that is tied to it, which is a distance time graph. This one's an easy graph. Distance is on the y-axis, time is on the x-axis. And there are only two types of lines that you'll see. Two types of lines that you'll see. A line going up, that means you're moving at a constant speed, and a line being horizontal, which means you're at rest. Before I continue any further, one of the most important properties of any graph is the slope, or what we call the gradient of the graph. The gradient or the slope is the angle of that line. The steeper the line is, the higher the gradient. The less steep the line is, the lower the gradient. How do we calculate that slope? It's y2 minus y1 over x2 minus x1. Some of you know it as rise over run. That's fine too. But since the y-axis of this graph is distance and the x-axis of this graph is time, so you're going distance over time, the slope actually gives you speed. So the steeper the line, the faster you're going. The less steep the line is, the slower you're going. But that also applies to curves, not just straight lines, to curves. If the line curves, it's no longer constant speed. If it's a straight line, it's constant because the slope is the speed and the slope is constant, so the speed is constant. But if the slope is increasing, this means the speed is increasing. And if the slope is decreasing, it's getting less steep, the speed is decreasing. It's getting less steep. You cannot, for now, you cannot calculate the value of the acceleration or deceleration from a slope. But you can just identify and describe the movement as speeding up or slowing down, speed increases or speed decreases. We have another graph that shows us the value of the acceleration. You'll see it now. Speaking of acceleration, it's defined as the change in velocity per unit time. It's the change in velocity per unit time. Remember, velocity is the vector version of speed, which means the speed can either increase or the speed could decrease or the direction could change. All of these are called acceleration. It's calculated using a very simple formula, which is delta V over T or V minus U over T. Now, I don't care which form you use. I'm personally biased towards this, because delta means change, by the way. You could also say v2 minus v1 over t, that's also fine. But I want you to understand, v means the final velocity. U is often used for the initial velocity. Essentially, it's the change, the difference in velocity over time. By the way, acceleration has a sign. Positive acceleration means the speed is increasing. Negative acceleration means the speed is decreasing. So when something's decelerating, we call it negative acceleration. We call it negative acceleration. But we just use the term deceleration to save ourselves a few more brain cells. Okay? Whatever we have left of those. Next, let's talk about speed time graphs. Arguably the most important, the most nuanced, and the most challenging part of, these kinds of questions. With a speed time graph, you have different types of things that you see. Speed is on the y-axis, time is on the x-axis. So you see 4 different types of motion here. You can see acceleration, constant speed, deceleration, or being simply at rest, depending on if the line is going up, it's horizontal, or if it's going down. Just like before, the slope represents something. In this case, the slope represents the change in speed or change in velocity over time. Change in speed over time is what? Acceleration. So the steeper the line is, the higher the acceleration. The less steep the line is, the lower the acceleration. The area under the graph is another very important factor in speed time graphs because it shows you distance. So if I ever ask you, get the distance traveled from the speed time graph, get the area under the graph. Which area? Depends on the question. I could specify a certain time for you. I can say, okay, from 0 to 2 seconds, or from 2 to 5 seconds, or I can say the total area. But regardless, there are 3 areas that you need to remember. 3 shapes. A triangle, which is half times base times height. A rectangle, which is base times height. And a trapezium, which is base 1 plus base 2 over 2 times height. If you forget the trapezium, like if you forget that rule, that's fine. You can just split that shape into triangles and rectangles, get the total area, and just add them together. This type of graph also has curves. But now, because you have the line can go up or down, unlike a distance time graph. In a distance time graph, the line can only go up. So it's either increasing or decreasing, but still going up. Here, it could be increasing as it's going up, decreasing as it's going up, increasing as it's going down. The word increase doesn't mean the value is increasing. It could mean that, but it means the slope is increasing, like it's becoming steeper. But this is called increasing acceleration because it's accelerating, but the slope's increasing. So increasing acceleration. This is called decreasing acceleration because it's still accelerating, but the slope is decreasing. This is called increasing deceleration because it's getting steeper. This is called decreasing deceleration because it's still deceleration, still slowing down, but the slope is getting less steep. All right? Now, let's solve a question. Actually, no, before we solve a question, I want to remind you of something. Sometimes, very rarely, and I mean very rarely, and I mean, okay, I'm not going to repeat myself. Questions can ask you to, look at how much I'm zooming in. You can see it's important. Questions can ask you to find the value of the acceleration from a sloped speed time graph, curved speed time graph. The way we do this, let's say, for example, it tells you, hey, find the value of the acceleration, not the average, huh? Just find the value of the acceleration at 2 seconds. So at the 2-second mark, we draw a tangent to that slope. We draw a tangent to that slope. If you're asked to find the acceleration at a specific part of the curve. If it's not a curve, that's fine. You don't need to draw the tangent. But if it's a curve and I want a specific value of the acceleration at a point on the curve, you get the tangent, you draw a tangent, and then find the slope of the tangent. Find the acceleration of the tangent, y2 minus y1 over x2 minus x1. Just find that using the first and the last line, for example, first and last point. Okay? Yes, it's only for a speed time graph, because that tangent will give you the acceleration. The value of the acceleration at that point, because the acceleration is not constant. Let's solve a question now. There will be a range. Anything that you have to draw will always have an acceptable range of answers. Yes. A car accelerates uniformly in a straight line at time t equals 0. So constant acceleration, I can tell that. At time t equals 3.2, and it starts from rest, so your initial speed is 0. At 3.2 seconds, the speed is 13. What's the acceleration? This one's nice. Change in velocity over time. So that's 13 minus 0, so find minus initial over time. That's 13 over 3.2. That's 4.06. I like to write my answers down to 3 significant figures, always. Meters per second squared. That's the unit for acceleration, meters per second squared. Explain in words what's meant by the term acceleration. Explain in words what's meant by the term acceleration. It is the change in velocity per unit time. Do not say change in speed. Change in velocity per unit time. Next. A car travels at 13 meters per second from 3.2 seconds to 12 seconds. Look at this, look at this. Keep in mind, earlier in the question, it accelerates uniformly from rest, but at 3.2 seconds, the speed is 13. So accelerates until it's 13. But then it continues to travel at 13, a constant 13, from 3.2 to 12. Plot the speed time graph for the car. Okay, so let's go. My starting value is 0 and 0. At 3.2 seconds, let's find that. Okay, how do I find that? Every small square is 0.4, by the way, on the x-axis and the y, but every small square is 0.4. So this is 2.4, 2.8, 3.2. This is 3.2. At 3.2 seconds, he was traveling at the speed of what? 13. So where's 13? I see 12 and I see 14. So 13 has to be perfectly in between. Perfectly in between two values. So I'm going to plot that value first. So blah, 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 going up, going up, going up. Oh my, I've already lost focus. Okay, cool. Here, that point. But then traveled at a constant speed of 13 until we hit a time of what? 12 seconds. So that's my final thing. Do not extend it beyond the 12. I have no idea what happens after 12. So I'll draw a straight line going up, because that was the description, the beginning of the question. Travels at a constant acceleration until it reaches a speed of 13 at 3.2 seconds. And then from 3.2 seconds to 12 seconds, constant speed. Good. Next. Determine the distance traveled by the car between 0 and 3.2. Look at this. Distance means area on the graph, but which area? Not the total. He wants it between 0 and 3.2. So I'm just going to highlight. It's not part of the answer, but I'm going to highlight that shape so you can see it. What shape is this? Starts with a T and ends with a triangle. It's a triangle, okay? So triangle, which is half times base times height. What do I mean by base? This is your base. So that's 3.2. So half times 3.2 times, what's the height? All of this is your height. That's 13. Let's work this out. half times 3.2 times 13. That's 20.8. Now, I don't know what the unit is, so I'm going to go back to the graph and look at the units used for the speed. It's in meters, so meters it is. Very good. So that's a nice speed time graph question with acceleration and area under the graph. Another big checklist. Forces is a very important chapter. Extremely important. So let's go ahead and revise. Okay? This one's easy. First, let's talk about Hooke's law. What is Hooke's law? Before we talk about Hooke's law, what's Hooke's law? If you apply a force on an object like a spring, it stretches. It will what? Stretch. The load is the force that you apply. And the extension is the increase in length. So it's the change in length. So extension is the difference between the stretched length and the original length. That's easy enough to understand. Obviously, as I increase the force, the extension will also increase, which means they are what? Directly proportional. If you take a look at this graph, as the force increases, the extension also increases, which again makes sense. This law is called Hooke's law. It states that the extension of a spring is directly proportional to the load on it, as long as the limit of proportionality is not exceeded. So what is the limit of proportionality? It's this point over here. This is the maximum force or the maximum extension that the spring can handle and still go back to its original length. Because if you remove the load, the spring should go back and contract to its original size. If you exceed the limit of proportionality, the spring permanently deforms. The spring permanently deforms. Forever. It does not go back to its original length. We always draw it curving towards the extension. So if this was an extension force graph, it would be a straight line until the limit, but then it would curve up. It always curves where the extension is. Now, finally, there's a formula for Hooke's law. It's K equals F over X, or my personal favorite is F equals Kx. It's easier to remember for me. F is the force, X is the extension, K is the what? The spring constant, defined as the force per unit extension. If you remember, we used to say that K represents the stiffness of the spring. K represents the how hard is the spring. So the greater the stiffness, the stronger the spring is. Okay, good. Next up, we already went over getting the resultant force when we discussed vectors, but we're just revising this again. If you have forces along a straight line, because this will be relevant later, if they're in the same direction, you add them. So the resultant force is 12 in this case. If the forces are in opposite directions, you subtract them. So the resultant force here is 8 newtons. Both of these are to the right. So the direction is to the right. Next up. This chapter primarily focuses on Newton's laws of motion. So how do forces affect motion? Before we do, there are some forces that really affect motion, like friction, right? Sometimes we call friction drag or air resistance or water resistance or, life resistance. Doesn't matter. There's always going to be friction. Okay? What does X represent? Okay, hold on. I'll go back. What is friction? If you have two surfaces in contact with each other, and they're not moving, that's fine, no problem. If one of them moves with each other, because of the roughness of the surface, like let's say you have a box on the ground, it's never perfectly smooth like this. If you zoom in, it's actually kind of a rough-ish surface, and the box itself is also kind of rough at a microscopic level. This interaction between the two surfaces creates friction. This frictional force, however, is always opposite to your direction of motion, which is why we call it a resisting force. Which is why we call it a resisting force. Okay. So it's always opposite to your direction of motion. It tries to slow you down, and it always produces heat. So if you rub your two hands against each other, it'll get hot because of friction. It converts the energy to heat energy. Friction with the air or with water is called drag. Sometimes the question calls it air resistance or water resistance. It's all the same thing. But drag, especially when it comes to air, okay, is affected by two properties. Speed, which means if your speed increases, if you're moving faster, the frictional force on you increases. So the drag force on you increases because you're colliding with the air molecules more often. And second, it's the area. The larger the surface area, so if I have a Lamborghini, you know how those all those TikTok influencers keep bragging about how they have Lambos, but I don't want a Lambo, frankly. I want a big, nice, 4x4, you know, nice chunky car, something that can handle some rough terrain. Why? Because I like boxy things, and that's me. But a Lambo has a much smaller what? Surface area. My nice big 4x4 Jeep or something has a much larger surface area. So the Lambo experiences less air resistance, whereas my big, nice, chunky, beefy car experiences more air resistance because it collides with more air molecules. So keep that in mind. If the area increases, the drag force also increases. By the way, in engineering, we call this aerodynamics. I'm sure some of you really are interested in cars, knows what that's called. Before I continue, I'll answer a few questions. What does X represent? X represents the extension. X represents the extension. The load is called the force. X is the extension, and K is the spring constant or the stiffness. All I'm saying here, and in the entirety of Hooke's law, is if you increase the force on a spring, if you increase the force that you're using to stretch, the extension increases. The ratio between them is always constant, and that's what's called the spring constant. Okay? But up until the elastic limit. Beyond the limit, that doesn't apply anymore. The term often used in exams is the spring no longer obeys Hooke's law, meaning we've gone beyond the limit. So it's no longer proportional. Now, let's go over Newton's first law. What is Newton's first law of motion? You find the limit of proportionality from the graph, or it's always given to you. It states, and you don't have to memorize the statement, by the way. Do not memorize the statement. Just understand what can happen. An object either remains at rest or continues in a straight line at a constant speed unless acted on by a resultant force. What do I mean? I mean that if the resultant force on an object is zero, meaning if I have a car that's at rest and then I decide to push it with a 10 Newton force to the right, and you decide to push against me with a 10 Newton force to the left, it stays at rest. But if the car has already accelerated and it's already moving pretty fast, if the driving force of the car is 1,000 newtons and air resistance eventually increases to also become 1,000 newtons, these two forces cancel out and the car continues to move at a constant speed and direction, so constant velocity. This is the part that confuses some people. They say, Mister, if this is 1,000, this is 1,000, so they cancel out. It should stop. No. Cars don't stop because the resultant is zero. Cars stop moving because there's a force that stops them. Here's the second part of the first law that is very important. What if the force is not zero? What if there is a resultant force? Well, depending on the direction of the force, you have three different scenarios. Scenario one, car is moving to the right. The forward force is 100 newtons, the backward force is 50, which means the resultant force is 50 forward. If the force is forward, the car speeds up. It accelerates. Let's say the same car is moving to the right, but then you press the brakes. So now there's a 50 Newton force backwards. You're still moving forward, but the force is backwards. You don't just suddenly go back. You still move to the right, but the speed decreases until you stop. You decelerate. Again, this is the part that confuses some people. Just because the force is backwards doesn't mean I have to move back. No. If I'm moving forward and the force is backwards, like air resistance or something, I slow down. I slow down. But if I'm moving to the right, this car got really chunky all of a sudden. And then you don't apply a forward or a backward force. You apply a force that's sideways. Perpendicular. The term used here is perpendicular to the motion. This car will end up changing direction. So the direction of the resultant force affects everything. If it's forward, you speed up. If it's backwards, you slow down. If it's sideways, like left or right, you change direction. You turn, you go in a circle. Very good. Now, that's Newton's first law. Let's go on to Newton's second law. Second law is very easy. In Newton's second law, that's literally it. This is the second law. It's an equation, F equals ma. But keep in mind, the force that we have here is always the resultant force. The force that you have here is always the resultant force. So after you subtract or add, that's what you put in. M is the mass, and A is the acceleration. So it's just the formula. Okay? Now, does the acceleration have to be in meters per second squared? Yes, it has to be. Please type your questions in chat. Very good. And the force is always in newtons. And the mass is always in kilograms. You must use SI units. This section is technically over, but there are very special types of motion that we need to discuss. There are two types. Circular motion, when things go around in a circle, all right? And objects that fall, if they fall in a straight line, okay? First, circular motion. When an object goes around in a circle, this is a continuation of what we just said earlier. Remember when we said if a car is moving to the right, but the force is sideways, it changes direction? Or perpendicular changes direction? What if it continues to change direction? It'll keep going in a circle. Circle, and so. If you're moving in a circle, the force is always towards the center of the circle. No matter where you are in this circle, I'm not going to make the car any prettier, to be honest. This is fine. It'll always be towards what? The center of the circle. But what about the direction of the acceleration? Because acceleration is a vector. The car is accelerating, by the way. Like, why is it accelerating? Because if the velocity was initially to the right, and now it's going down, and now it's going up, you're now changing the direction of the velocity. So if the direction is changing, is the velocity changing? Yes. So the velocity changes. And if the velocity changes, you are accelerating. You have an acceleration. And the direction of this acceleration is also towards the center of the circle. The force and the acceleration are always in the same direction, no matter where you go. Now, going in a circle has a few caveats. The force that you need to stay in a circle depends on three things: your speed, the radius, right? And your mass. If you move faster, like if I press the gas and try to move faster, I will need more force. So if the speed increases of the car, I will need more force to stay in my circle. This one makes sense. So let's look at the other one, the radius. If I'm going around a very large circle, that's easy. That's not a problem because I can take my time changing the direction. But if I'm trying to take a U-turn, like if my car is moving in a straight line and all of a sudden I want to take a sharp turn, like I'm going up and then suddenly I want to go down. This needs more force. This needs a little force. This needs a big force. Why? Because you want to change the direction in a very short amount of time. It's a very large acceleration, which is why if you're driving, even a bike, and you want to take a sharp turn, you need to slow down first. Otherwise, if the radius of that turn is too small, you're going to need more force. And the friction on the ground might not give you enough force. Which is why usually, if a car is moving very fast and it takes a sharp turn, it doesn't stay on the road. It goes off-road. Have a nice day. You're gone now. Okay? Good. Finally, if your mass increases, you need more force. This comes from F equals ma. If you have a big truck, it needs a lot of force to turn. But if you have a bike that you're riding, like a bicycle, it needs less force. That also makes sense. It's very easy to understand. So the more mass the car has, the more force it needs. And the smaller the mass an object has, the less force it needs. Good. Now, before we talk about falling objects, I'll answer a question. When the force is against the car, when will the force against the car stop the car? If a car is decelerating, it will eventually reach zero speed. If a car is decelerating, it will eventually reach zero speed. And when it does, خلاص, it stops. Okay. Now, when it comes to falling, you have two versions of falling. If you're falling in a vacuum, as in there's no air resistance, this means you fall with a constant acceleration, 9.8. So if I say we're ignoring air resistance, again, if the question says we're ignoring air resistance, then you're falling always falling with a constant acceleration of 9.8. Done. Let's move on. Obviously, that depends on the acceleration of free fall of the planet. If it's a different planet, it's not 9.8. For now, it's 9.8. But if an object is falling in air, we go through the skydiver effect, which means you fall through 3 stages of motion. You have to memorize the 3 stages. If I say you're falling in air, there are 3 stages. Stage 1, you just jumped. There's no air resistance yet. So there's only weight that pulls you down. So you fall with a constant acceleration. Stage 2. Now there's a little bit of air resistance acting on you. But the weight is still more than the air resistance. But there's still air resistance acting on you. And as the speed continues to increase, that air resistance continues to increase. However, because of the air resistance, the resultant force decreases. The resultant force decreases. And according to F equals ma, if the F decreases, the A decreases. Because force affects the value of the acceleration. The proportion. So the acceleration decreases. Final stage. Now, again, you haven't opened the parachute or anything, but eventually the air resistance increases so much, it becomes equal to the weight. The weight and air resistance are equal. So you fall at a constant speed. We call that speed terminal velocity. That happens when the weight is equal to air resistance. If you sketch a graph for this motion, this is what it looks like. A short straight line, then it curves until it's a constant speed. Now, if there's a parachute, and you open it, it suddenly drops your speed, and then you move at a constant speed again. That's if there's a parachute. Because the air resistance suddenly increases. I'm not going to write air resistance. You know it's air resistance. And it becomes greater than the weight. Now, a common question is, Mr. if the air resistance is greater than the weight, you go up. What did I say? If the force acting against you, if the resultant force is backwards or moving against you, you don't go up, you don't go back, you slow down. So here, if you open the parachute, the air resistance is greater than the weight, so the resultant force is upwards, so you slow down. But as you slow down, the air resistance decreases again and becomes equal to the weight again. Like it decreases until it becomes equal to the weight. And you fall with a new safe terminal velocity that you can land on the ground with. Good. Let's solve a question. This is a hard question. I know this class is like stretching a bit too long, but stay with me here. We're almost done. Now, this is a hard question, and it's hard because it tries to trick you with the concept of the resultant force. The concept of the resultant force. I remember getting this in a test before. Hardly anybody gets it. Figure 2.1 shows an object of mass 2 kilograms on a bench. This object is connected by a cord over a pulley to an object of mass 3 kilograms. When the object is released, when the 2 kilogram object is released, so you were holding it and then you let it go, it accelerates at 4 meters per second squared. So that's the acceleration. What is the resultant force acting on the 2 kilogram object? Yalla, what's the resultant force? F equals ma. So it's 2 times 4, which is what? 8. Yay. Easy question. And it's one of the few tricky questions because I'm not going to use this value ever again. And we move on. Now, or we might, I'll show you where. Calculate the upward force F exerted by the cord on the 3 kilogram object. This is something I'll mention later when we start solving past papers. But I want you to fear 3-mark questions more than 2 or 4-mark questions. Usually, if there's 3 marks to a question, there's a trick in there. Somewhere. Most of the time. Here's the thing. If I zoom in and I look at that 3 kilogram object, there are 2 forces acting on this object. The weight of the object, which is mg, because W equals mg, Look, we're using something we learned earlier. And that upward force F. I don't know what that upward force F is, right? I don't know what it is. You might say, it's 8. No, we don't know if it's 8. But what I do know is that the weight is greater than F. How do I know that? Because isn't that object accelerating at 4 meters per second squared? No, I didn't disconnect or anything. Oh, I'm giving your brain time to absorb this. You might say, but Mister, he said 2 kilograms is released and it accelerates at 4. But since they're connected, if this moves with an acceleration of 4 meters per second squared, isn't this also going to fall with an acceleration of 4 meters per second squared? So that's the first piece of information we have. We have the acceleration, which means we can use F equals ma. And the second piece of information, we have the difference between these two forces. So step 1, F is equal to ma. Step 2, what are the two forces? W minus F equals ma. Because the resultant, I said, F must always be what? This is something that trips a lot of people. F must always be the resultant. Always must be the resultant. So it's W minus F equals ma. Okay? Now, this question was back from 2022 because back then, the value of G was 10. So if you do open up a mark scheme and you try to solve along and you check the answer, the G here was 10. It wasn't 9.8. Keep that in mind. I'm going to solve it as if it was 9.8 because that's the new value of G. So starting 2023 exams, the G is 9.8. Well, what is W? Mass times G. Remember, this is mg. So mass is 3 times 9.8 minus F. I don't know what the F is. I'm going to find it. Equals, that sounded so wrong. Let's move on. Mass, which is what? It's still 3 kilograms times a, what's the acceleration? 4. The rest is just algebra. The rest is algebra. So let's go. 3 times 9.8 is a nice cozy 29.4 minus F equals 3 times 4, which is 12. And F is equal to, this goes here, 29.4 minus 12, which is 17.4 newtons. Honestly, this should have been 30, because it's 3 times 10. So 30 minus 12 is 18. Mark scheme is 18, but still. Again, just to remind you, why is it W minus F? Because the weight is greater than that force in the cord. So the resultant force is W minus the F, the weight minus the force in the cord. Now, the question is not over, because it has a part C. The objects have a constant acceleration. We know that. Thank you. Show that the speed of the objects after 0.8 seconds, it's giving me the time, after release is 3.2. He wants the speed. Guys, what was the acceleration from the previous step? Acceleration was 4, right? Meters per second squared. And we have the time. He wants the speed. Show questions are just like calculate questions, but he's given you the final answer. Maybe because I'll use it in the next bit. But acceleration equals change in velocity over time, which means the change in velocity is equal to acceleration times time. You have the acceleration. It's 4. You have the time. It's given. It's 0.8. That's equal to 3.2. So in show questions, you really need to show your working, like in detail, how velocity is equal to acceleration times time, and you show the substitution, how that's 4 times 0.8 is equal to 3.2. Just show the working. Okay? Final question here. Final bit of this question here. A card of width 2 centimeters is fixed to a 2 kilogram object. Now, this is another trick. He put a small 2 centimeter object, like card, to my 2 kilogram object. The 2 kilogram object moves to the left. And the card passes through a beam of light that is perpendicular to the card. Using the speed given in CI, calculate the time taken for the card to pass through the beam of light. This is just a bunch of mumbo jumbo and lots of talk for something much easier than what you expect. He literally gave us distance. He wants time. And he told us, go use a speed of 3.2 because that's the speed given in CI. Speed is distance over time. So time is distance over speed. Distance is 2 centimeters. It's in centimeters. So I need to change it to meters. It's in centimeters. So I need to change it to meters. So 2 divided by 100 gives us what? 0.02. So it's 0.02 divided by 3.2. Even it has to be in meters. This gives me 0.00625. Again, I like to keep all my answers to 3 significant figures, so that's okay. Seconds. Now, let's solve another question really quick. This one's easier though, much easier because it's about, can you write it in standard form? Absolutely. Let's answer these quickly. State 2 features of a vector quantity as magnitude, or I'm just going to say magnitude and direction. State the names of 2 other vector quantities. Now, he said force is a vector, so I can't use force. He said force is a vector, so I can't use a force. Okay? So what can I use? What can I use? You can use velocity. You can use acceleration. You can use momentum, any other quantity besides force. A student suspends a spring from a clamp and measures the length LO. The student then suspends loads of different weights from the spring and measures the length of the spring for each load. He then plots a graph of the length of the spring against the weight. Figure 2.2 is the graph that the student plots. So he's plotted the graph of length and weight. Using figure 2.2, determine the initial length of the spring. So the initial length means the length of the spring. Keep in mind, this is not an extension graph, it's a length graph. So what is the length of the spring before stretching? So what's this value over here? Ooh, I need to count. Each square is 0.02, by the way, because that's 0.2 for 10 squares. So that means it's 02, 04, 06, 08, 1, 1, 2. So 0.12. So it's 0.12 meters. State what is meant by limit of proportionality and use figure 2.2 to determine the weight of the load that causes the spring to just reach the limit. So the limit of proportionality is the maximum load or maximum force after which the spring, or we can say the extension, is no longer proportional to the load, right? Because after that, they're no longer proportional. It's no longer a straight line. The maximum force after which the spring is no longer proportional to the load. Now, him saying what is the weight or asking for the weight means what is the weight after which it starts to curve. This will usually have a range, by the way. It's a very small range, but it'll usually have a range. What I would do is I would get my ruler and overlap it over the line. Just so I can see, so my eyes have an easier time seeing, when did it start like curving away? Like, look at this. When did it start curving away? Roughly here, like here or here. So I'll use those as my points. I can use any one of these. Oops, my bad. So I'll just draw a straight line here because my eyes get all blurry here when I'm looking at graphs. And what's this value? This is 10, 10.2, 10.4, 10.6. So in this particular case, 10.6. You could, I think this had a range of like 10.4 to 10.8. Like there's a big range that's accepted here, but 10.6 it is. Next, using figure 2.2, determine the spring constant. Oh, this one's easy. I know it's a 3-mark question, but this is one of the few times where it's not really a trick, or is it? F equals kx, but k is equal to f over x. Pick any f and x you want, but as long as it's on the straight line, as long as it's on the straight line. So pick whatever point you want, as long as it's on the straight line. So I'm going to pick a point, some random point here. Why not? The randomest of random points. What is this value? Well, what's this random point that I picked up? Let's go. I'll pick this, and this is it. So my points are 0.2. So that's 2, 2, 2, 4, 2, 6, 2, 8. That's my y-axis point. And this is 1 squared before the 4. So that's 3, 8. 3.8. Because each square, again, is 0.2 on the x-axis. And this is a mistake some people will make. They'll go like, oh, mister, that's easy. K equals f over x. The force is, it was 3.8, right? Yeah, 3.8 over 0.28. Was it 2.8? Yes. Is that right? Is that right? What do you think? Bravo. 0.28 minus 0.12, because the y-axis here is the length, not the extension. The y-axis here is the length. So 0.28 isn't the extension at 3.8 newtons. It's the length. So 0.28 minus 0.12 to get the extension. You have to subtract the original length from the value. Divide by minus. These are the sounds my calculator makes in my head, at least. What's the unit that for the spring constant? It's the unit of F divided by the unit of x. So Newton per meter in this example. So Newton per meter. Before I lose the rest of my voice, let's finish up the last 2 pages in this sheet. It stretched longer than I expected, but still, let's go. Final thing, momentum. Very easy, yet very annoying questions for some of you, because it's hard to contextualize momentum quickly. But the important thing about momentum is this. If I ask you, what is momentum? It's just mass times velocity. It was Newton's way of trying to say, when an object is moving, the mass of the object is very important. It's not just how fast it's moving, it's how heavy it's moving. Because if a fast, heavy object does more damage than a fast, light object, same thing. But when they crash, the heavy object will probably win. So he just multiplied mass and velocity and said, hey, momentum is mass and velocity. This affects the motion of the object. His own words were, it is the amount of movement or motion of an object. Then, what is impulse? Impulse is force times time, or force times time for a collision, like a hit. So impulse isn't a force that's applied gently over a long time. No, 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 no. Impulse is a very momentary force. It's like when you slap something or punch something, all right? Or stab something, or some people might think I'm weird. Now, okay, good. Now, before I talk about why is it also equal to change in momentum, look at the next question. What is force? Force is also defined as the change in momentum over time. This is actually the original version of Newton's second law. Again, this is the initial version of Newton's second law, which is change in momentum over time. Because think about it, when you apply a force on something, it increases in velocity, or maybe it decreases in velocity. So it changes its momentum over time. But because force can also be equal to the change in momentum over time, velocity over time is acceleration, which gives us ma. This is why F equals ma and change momentum over time are both called Newton's second law, so it's fine. But if you make the change in momentum the subject, if I move the time up here, you end up with Ft equals change in momentum, which means impulse is also equal to the change in momentum. A lot of questions use this little distinction here for a trick. A question could ask you, calculate the momentum of the object, the change in momentum of the object, but it gives you force and time. It's a trick. It wants you to get impulse. A question could say, hey, here's the, what's the impulse of the object or on the object? But it gives you mass and velocity. It's the same thing. Impulse is force times time. Impulse is also equal to change in momentum. So change in momentum is equal to impulse. But if I ask you to define it, it's force times time. Okay? Finally, what is the law of conservation of momentum? You have to memorize it as is, because sometimes you have to define it and sometimes you use it. The definition is the total momentum of a closed system is always constant or conserved. What does that mean? This means that if you have, keep in mind, two objects colliding. In O-level physics, we will only have two objects ever colliding. Most questions involving momentum will have only one object. So we use all of these laws. For one object only, we use all of these. But if we have two objects colliding, we use the law of conservation of momentum, which is the total momentum before a collision equals the total momentum after a collision. Here's a quick example as to how we use it, and then we'll solve a question that has that same example, okay? So really quickly, if I have two objects, let's call them A and B. Let's say A is moving with a speed of 10 meters per second and has a mass of 2 kilograms. B has a mass of 1 kilogram but is at rest. This is before they collided. After they collide, question has to always tell you what happens after a collision. So after they collide, they could, I don't know, B could move and A could stop. A and B could move, but, you know, different speeds. A could rebound back, but B moves forward. Or A and B could stick together. There's different scenarios. Question has to emphasize what scenario this is. Let's say, for example, A moves a little bit slower at 1 meter per second. Let's make it 2 meters per second. And B moves to the right with the speed of V. These questions will always ask you to find V, find the velocity of that object after the collision. Solving it is simple. Sum of momentum before equals sum of momentum after the collision. So mv plus mv equals mv plus mv. Now, proper textbooks would tell you m1u1 plus m1u2 equals m1v1 plus m2v2. You don't have to think about what's u and what's v. Just get the momentums of each object separately, then add them. So this is 2 times 10, that's the mass times velocity, plus 1 times 0, so that's not moving, 0, equals. Remember, this has a mass of 2, this has a mass of 1. So this is 2 times 2 because the speed is 2, given, plus 1 times v, v is unknown. Solve for v. 20 equals 4 plus v. So v is what? 16 meters per second, which makes, oops, Should not be a square over there. There's this makes sense because think of it this way. Heavy object, it's a lighter object. Lighter object goes zoom. Makes sense, right? Let's solve a question or two. I have a couple of questions here. One with an object, right? Just one object, and then two objects as well. It depends on the question, keep in mind. And remember the impulse thing we just discussed. First one is nice. You have two railway trucks on a track. Truck A is 6,000 kilograms. B is 5,000 kilograms. This is moving at 5 meters per second. This is stationary. What is the momentum of truck A? This one's easy, mass times velocity, which is 6,000 times 5. 30,000 kilogram meters per second. The unit of momentum is kilogram meters per second because it's mass times velocity. So kilogram is mass, meters per second is velocity. Then the trucks collide, their buffers compress, and then they bounce off of each other, remaining undamaged. After the collision, truck B has a momentum of 27,000. This is a trick question. It didn't give us the velocity. It gave us the momentum immediately after the collision. Hey, I have a question. What was the momentum before the collision? Like I'm getting ahead of myself a little bit, but what's the momentum before the collision? 30,000, because B was stationary at 0. This is at 30,000. So the total momentum is 30,000. After the collision, truck B now has a momentum of 27,000, like given. Mass times velocity is now 27,000. What is the impulse applied to truck B? Remember what I said? This is usually a trick. I don't have force and time, but I know that impulse is change in momentum, delta mv or delta p. Oi, B had a velocity of 0, and now it's 27,000 momentum. So the change is 27,000 minus 0, which is 27,000. Yay. Now, what's the unit? I know that impulse is force times time, which means its unit should be Newton second. But you can also use kilogram meters per second. They're the same unit. I won't go into details as to how, but they're the same units. If you want to use Newton second or kilogram meters per second, they're both fine. Next. Now we get to use force times time. The trucks are in contact for 0.6 seconds. He's given me the time. What is the force? Oh yeah, I know that one. Force is equal to the change in momentum, delta P over T. What's the change in momentum? Oh, that's easy. Impulse. 27,000. Over, what's the time? 0.6. This will probably give me a big value. Yeah, 45,000 newtons. Huge force. Okay? So force is equal to change in momentum over time. Next, calculate the final speed of truck A. Wait, what? Why does he want truck A? Just listen to the dude. How do I solve this? Easy. Total momentum before equals total momentum after. Now, I already know that the total momentum before the collision, because B was stationary and A was moving, is 0 plus 30,000. What about after the collision? After the collision, B was moving and I already have the momentum, which means what's the momentum of A after the collision? I'll call it mv for now. What's the momentum of A after collision? So the mass times velocity of A after the collision is equal to 30,000 minus 27,000, which is 3,000. That's the momentum. I don't want the momentum. I want the speed. So if mv for A is 3,000, because that's the change in momentum. That means V is equal to 3,000 divided by 6,000, because the mass of A is 6,000. It's on the question, which is 0.5. So 0.5 meters per second. Makes sense. A is kind of heavy, right? And after it bounces off, it probably lost a lot of energy. It's moving slowly. Final question. Fine. I promise. There's nothing more than this. Can the momentum be negative? Yes, but we'll see that when we solve past papers. Or here, right now. Figure 3.1 shows a boy throwing a ball at an object in a fairground. These things are always rigged, by the way. Like they have screws in here that keep them fixed, so you never win. With a little bit of a spring, so it goes back and forth and makes you think you're winning. The ball has a mass of 190 grams. Keep that in mind. And it travels with a constant speed of 6.9. Calculate the momentum. So mass times velocity. But first, I'm going to change this to what? To kilograms. I don't like using non-SI units for these things. So I'll divide this by 1,000, which gives me 0.19 kilograms. So mass times velocity, 0.19 times 6.9. 1.311. So 1.31 is fine. Kilogram meters per second. You asked, can the momentum be negative? Now, look closely. After hitting the object, the ball bounces back along the same straight line, but with a speed of 1.5. This is very important. If you ever see the term bounce, rebound, like whatever it is, this means that this new velocity or momentum will have a negative sign, because remember, moving to the right is considered positive, for example. Moving to the left is now considered negative. The sign changes. This will be very important when we solve. So almost always in momentum questions, if you see a single object bouncing or rebounding, you need to give the bounced speed a negative sign. You'll see what happens. The object now has a mass of 1.8 kilograms. What is the speed of the object after it is hit by the ball? So what is the speed of the object after it is hit by the ball? This is a collision question now. This has changed the collision question. Unlike the previous one, where he sketched like the collision happening, here there is no sketch. It's just like, hey, look at this. My advice, sketch it. Here's the ball. Here's the weird object. My art isn't like the best at the moment. This is before the collision. This is moving to the right. This is stationary. After the collision, the ball bounces to the left, but the weird object moves to the right. Look at the language again. After hitting the object, that's called the object. This thing was the object. The ball bounces back, all right, with a speed of 1.5. So the momentum here is 1.31 plus 0 equals, the speed here was 1.5, but the mass of this object is 1.8. I don't know what the speed is. What is the speed of the object after it is hit by the ball? So again, we calculate the new momentums. Remember, this has a mass of 0.19 kilograms. So it's mass times velocity plus mass times velocity. 1.31, because that's the momentum before the collision, equals 0.19 times negative 1.5. This is vital. The direction has changed. So you need to change the direction of the velocity by changing the sign from positive to negative. You have to. This only happens in these types of questions. You have to. Plus, what's the mass of the object? 1.8 times V. The rest is basic algebra. So 0.19 times negative 1.5. This gives me, I'll tell you something. Some students, when they solve, think they're doing bad because the numbers look weird. Like, what's this? 0.285 and 131. Like, You're not doing bad. You're not doing badly at all. Sometimes the questions are designed to have really crappy numbers. This is fine. So 1.31 plus 0.285, because I'll move this to the other side, gives me 1.595 divided by 1.8. This goes to the other side of the plus, then 1.8 goes to the other side by dividing it. And so divide that by 1.8 leaves us with 0.886 meters per second. Okay? You are not doing bad. The numbers just are weird in this question. So you had the right, you asked the question right time. Can momentum be negative? Absolutely. I think that's enough for today, right? Enough for part one.